my name is Alexander Trautsch, and I'm presenting cooperative work between myself, Steffen Herbold, and Jens Grabowski. Static source code metrics and static analysis warnings for fine-grained just-in-time defect prediction. Now, you may know static source code metrics from the literature or from release-level defect prediction, sometimes called long-term defect prediction. They encompass things as size and complexity and coupling between objects, for example. And they are usually attributed to have an impact on software quality. Now, static analysis warnings, on the other hand, if you program in Java, you may know some of these tools. They are available for developers to check their code for common coding mistakes or style violations and best practice violations. And they are part of software best practices, so they also have a relationship to software quality. And most of these tools can also be integrated into the common development workflow. For example, PMD can be integrated into GitHub, and you can directly see warnings from PMD for your pull requests or every change, basically, that you do to the repository. Now, fine-grained just-in-time defect prediction, the basic idea here is that we collect information from the past, in this case, files within changes. As they are in the past, we know which one was responsible for a bug that later has to be fixed in the software. So we collect these past changes, build predictive models, and are then able to classify a new incoming change as clean or being risky of introducing a bug. The difference between fine-grained just-in-time defect prediction, as introduced by Pascarella and colleagues, is that for the normal just-in-time defect prediction, usually you have the commits as instances for your predictive model, and for the fine-grained just-in-time defect prediction, you have the files within the commits for your as your instances for your predictive model. The recording of these past changes also introduces their own metrics, which we call just-in-time metrics here. They are things like, for example, developer experience, or how often the file has been changed, or how long ago the last change to this file was. Now, how do we label these past changes as being responsible for introducing a bug or not? In the literature, there are two basic approaches. The first one is a simple keyword-based approach, where we are searching in the commit messages for keywords, for example, fix bug. If one is found, all changes contained in this commit are labeled as bug fixing. The things they are changing is traced back to the all change that introduced this part of the code. And this is then labeled as defect inducing. The second approach requires a valid link from the bug fixing commit to an issue tracking system. The issue has to be of the type bug. And the basic idea here is that with the additional information from the issue, for example, the issue lifetime, we can introduce suspect boundaries where we say, okay, if this change has happened after the bug was known, it is most likely not the change that induced this bug. Before we come to the research question, a quick overview of our data. We have 38 Java projects with all changes and all files. Due to previous work we did, we have some manually validated data in this data set. For example, the issue types are manually validated. We are implementing the two labeling strategies from the literature, the keyword-based ad hoc ACC approach and the issue type system approach, which requires a valid link to the issue tracking system. We are inspecting 4 sets of features: the just-in-time based features, static source code metrics, and PMD static analysis warnings, and also all of them combined. Now, the first research question is obviously, how do these new features, static source code metrics and PMD static analysis warnings, are correlated with defects in comparison to the default just-in-time defect prediction metrics? To evaluate this, we trained a regularized logistic regression model on all data and a random forest classifier, and then inspect the resulting coefficient values in case of the logistic regression model and feature importances in case of the random forest. And we find that static and PMD feature sets are contained in the top 10 features in 4 out of 3 combinations, so that they are likely to improve just-in-time defect prediction itself. The next question is, can these new types of features improve just-in-time defect prediction? To evaluate this, we are running a just-in-time defect prediction experiment with a sliding window approach, We're using 3 months of data for the training, 1 subsequent month of data for evaluating the model, and then rank the resulting performance of the models. We can see this in figure 4. The combined feature set is ranked first in every case, but only statistically significant in 3 out of 4 cases. However, the difference to just-in-time defect prediction metrics is statistically significant in every case. So we conclude that the combined feature sets can improve just-in-time defect prediction. For the last research question, we wanted to ask if these additional features can improve cost-saving potential of the resulting predictive model. For this, we are using a defect prediction cost model introduced by Steffen, which gives us upper and lower boundaries for which the model is able to save cost. And as we can see, the combined feature set is no longer ranked first. However, it is still statistically significant different from only the just-in-time defect prediction models. We can also see that static is ranked first in 2 cases and PMD is ranked first in 1 case. To summarize our work, we conducted a fine-grained just-in-time defect prediction experiment. On 38 Java projects, we introduced 2 new feature groups. One, static source code metrics, which is used commonly in the literature for release level defect prediction, and PMD static analysis warnings as another feature group. We evaluated everything on the 2 common labeling strategies from the literature, the keyword-based SCZ approach and the approach where you will require a direct link to the issue tracking system. We find that the combination of all features is ranked first in model performance, however, only statistically significant in 3 out of 4 cases. The combined feature set is also able to save more cost than only the fine-grained just-in-time features. We also found that the labeling strategies themselves have a bigger impact on model performance than the feature groups. This is probably due to the fact that the keyword-based approach just finds a lot more true positives for the instances, for the predictive models. The one-line summary would be that the static source code metrics and static analysis warnings from PMD significantly improve model performance and also cost-saving potential.